Hello friends, good afternoon and welcome to the set live lectures. Dear friends, as you know that we have started a series on polynuclear hydrocarbons and heterocyclic compounds, and today we are conducting yet another lecture in the same series. In today's lecture we will be talking about derivatives of pyridine and indole derivatives. To discuss this topic we have with us our subject expert Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry in Dal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you so much ma'am. Hello viewers, in this series of polynuclear hydrocarbons and heterocyclic compounds, we have discussed many compounds like anthracene, we have discussed pyridine, thiol, indole. In today's lecture, I will discuss about the derivatives of pyridine and indole derivatives. As we are aware, we have discussed in detail about the nature of pyridine, that pyridine has nitrogen atom and it has lone pair of electron, and these lone pair of electron is responsible for the kind of reaction pyridine gives, like it gives electrophilic aromatic substitution reaction and nucleophilic aromatic substitution reaction. But in what extent they are giving these kind of reaction, we will discuss in detail in today's lecture. Today's lecture plan is pyridine is bad at electrophilic aromatic substitution. How? Alkyl and aryl pyridines, halopyridines, aminopyridines, pyridine N oxides are reactive towards both electrophilic and nucleophilic substitution reactions. Halopyridines, which are also known as pyridinols, pyridine aldehydes and ketones, pyridine carboxylic acids, significance of pyridine derivatives, then derivatives of indole like indoxyl, icetin, indigo, 1-hydroxy benzotriazole, or we can also say HOBT in short. Nitrogen has lone pair of electron, but what is the most important thing in pyridine, that it does not participate in delocalization. So pyridine is bad at electrophilic aromatic substitution. Why? You can see that nitrogen atom destabilizes the cationic intermediate formed especially when it can be delocalized onto nitrogen. You can see the delocalization, and this is the unstable electron deficient cation, and you can see unstable electron deficient cation because of this positive charge on nitrogen atom. Pyridine does not undergo electrophilic substitution reaction readily. Why it is so? Pyridine aromatic substitution on pyridine is not a useful reaction. The reaction is unreactive and the electrophilic reagent attack nitrogen, making the ring even less reactive. Avoid nitration, sulfonation and Friedel-Crafts reaction. These are the general electrophilic substitution reaction on simple pyridines. The normal reagent for electrophilic substitution reactions such as nitration are acidic. Treatment of pyridine with usual mixture of nitrating mixture, that is HNO3 and H2SO4, merely protonates the nitrogen atom. On the other reactions such as Friedel-Crafts acylation require Lewis acid, and these two react at nitrogen atom. Hence, you can see this kind of pyridine complex which is stable found while react with this acyl chloride. So, no further reaction can form because it is a stable intermediate. Rather than this, pyridine is a good ligand for metals such as aluminium or tin, and once again the complex with its cationic nitrogen is completely unreactive towards electrophiles. Nucleophilic substitution is easy with pyridines. Why it is so? Because nitrogen atom makes pyridine more reactive at position number 2 and position number 4. Why it is so? Because it lowers the LUMO energy, lowest unoccupied molecular orbital. You know, when these energy or these orbitals are formed by the atomic orbitals, these are the molecular orbitals LUMO and HOMO, highest occupied molecular orbital. So, it lowers this energy, this molecular orbital energy of the pi system of pyridine. And mechanism for the displacement of halogens in these positions by nucleophile is as follows. You can see how the reaction takes place, how the nucleophilic substitution reaction takes place in pyridine. So, this is pyridine with this chloride ion at this ortho position or position number 1. You can see first of all it attacks to this position because of this electro withdrawing nature of this nitrogen atom, and then you will get this kind of tetrahedral intermediate and finally the substituted product. The intermediate anion is stabilized by electronegative nitrogen atom and by delocalization around the ring. These reactions have some similarity to the nucleophilic aromatic substitution, but are more similar to carbonyl reactions. We have discussed in earlier lecture about aldehydes and ketone, how they react and how they proceed by nucleophilic substitution reactions. The intermediate anion is a tetrahedral intermediate, as we have shown here, that loses the best leaving group, and this is chloride, to regenerate the stable aromatic system. Nucleophiles such as amines or thiolate anions work well in these reactions. These are the another nucleophilic substitution reaction. Here you can see chloride ion is substituted by NH2 amine group, and here you can see this chloride ion is substituted by this SR group. The leaving group does not have to be good enough in these reactions. Continuing the analogy with carbonyl reactions, 2 and 4 chloropyridines are rather like acid chlorides, but we need only use less reactive pyridyl ethers which react like esters to make amides. Now, alkyl and aryl pyridines. The first derivative we are talking about of pyridine. Many alkyl pyridines are obtained from coal tar and from the pyrolysis of natural products. 2-methylpyridine from anabasine, 3-methylpyridine from nicotine, 4-methylpyridine from spartine, etc. A mixture of 2 and 4 alkyl pyridine is obtained by the Ledenberg rearrangement of pyridinium salt as shown in this reaction. You can see this is the pyridinium salt with N positive charge and X negative, and at this temperature you will get these two, it is a mixture of 2 and 4 alkyl pyridines. The reaction of Rx with pyridine with a strong base, normal butyl, lithium butyl, yields predominantly the 2 alkyl isomer. You can see here. On the other hand, in the presence of free metal, for example lithium or magnesium, alkylation of pyridine by Rx alkyl halide occurs exclusively at position number 4. 2,6-dialkyl pyridine can be obtained by following sequence. You can see how the reaction proceeds when it reacts with CHCl3 chloroform, NaNH liquid ammonia, and further with tertiary butyl lithium, it will give you 2,6-dialkyl pyridine. The decarboxylation of alkyl substituted carboxylic acids is another method for the preparation of alkyl pyridines, but the yields are unsatisfactory. Now, picoline, 2-picoline is a liquid, boiling point 129.4 degrees Celsius. You can see the structures of picolines. You can see this is alpha picoline, also known as 2-picoline, beta picoline because of this methyl group at position number 3, or we can say position beta position. This is 3-picoline, this is gamma picoline or 4-picoline. 3 and 4 picolines have higher boiling points. All the 3 picolines are miscible with water, while ethyl pyridines and lutadines are only partially miscible. The hydrogen atom in toluene are only weakly acidic, while in 2 and 4 methyl pyridines are much more acidic and are more potential carbanion sources. Deprotonation means removal of proton of 2-methylpyridine by an organolithium gives 2-pyridyl methyl lithium. You can see here, which is a useful nucleophile in the manner of a Grignard reagent. So, you can see how this carbanion first of all formed. It is also called nucleophile and it attacks to this carbonyl carbon, as we are aware that carbonyl carbon has a tendency of forming electrophile because of this electro withdrawing nature of oxygen. And you can see this kind of addition product followed by hydrolysis, you will get this kind of product, unsaturated product. It reacts with aldehydes and ketones to give alcohols which can be dehydrated to vinyls, pyridines, carboxylic acids are produced with carbon dioxide and reacts with alkyl halides, etc. 2-alkyl pyridines are useful starting materials for the synthesis of bicyclic system. Thus, the halogen carbonyl compounds, they give indole. You can see how the reaction proceed. The electron deficiency caused by electronegative nitrogen atom at the position 2 and 4 of pyridine also permits nucleophilic reagents to add in a Michael type reaction. We have also discussed Michael type reaction in aldehydes and ketones. To vinyl substituent attached at position number 2, 4 but not at position number 3. 2-vinyl pyridine on ozonolysis gives formaldehyde and pyridine 2-carboxyldehyde. You can see how the reaction proceed or Michael type reaction. With the characteristic nature of this nitrogen electron withdrawing nature, this carbanion, or we can say this carbethoxy carbanion or nucleophile attack to this carbon, and you will get this kind of addition product, followed by rearrangement you will get this kind of product. 2 and 4 alkyl pyridines are oxidized by a variety of oxidizing agent to the corresponding carboxylic acid. That is, alkyl group get converted to the carboxylic group. 3-methyl pyridine in contrast is not oxidized and also is unreactive towards phenyl lithium and is rather furnishes 3-methyl 2-phenyl pyridine. The reaction of 3 alkyl pyridines are expected to be similar to benzene derivative having a methyl group meta to an electron attracting group. 2 aryl pyridines are best prepared from the appropriate aryl lithium and pyridine, and 4 aryl pyridines are obtained via Hench synthesis using an aryl substituted starting material. We have discussed it, pyridine also. 3-phenyl pyridine is best obtained from 3-aminopyridine and reacting it with pentyl nitrite in benzene. Monophenyl pyridines are high boiling point liquids. Oxidation with KMnO4 benzoic acid is obtained. These results differ from that of quinoline, where the benzene ring is always destroyed to yield pyridine carboxylic acid. Electrophilic substitution always takes place in benzene ring. Another derivatives of pyridine are halopyridines. All the monohalopyridines are known as and can be prepared by the direct halogenation of pyridine of replacement of the diazonium group by Sandmeyer reaction. 2 and 4 derivatives may also be obtained by displacement of hydroxyl group with phosphorus pentachloride. Here you can see this is the reaction which is showing the tautomerism in halopyridine. This is the alcoholic group and this is the ketonic group, and when it reacts with phosphorus pentachloride it will give you this kind of product, that is chloro at ortho position. 3-halopyridine cannot obtain in a similar manner as we have obtained 2-halopyridine. 3-bromopyridine may obtain by mercuration of pyridine followed by bromination. That is, first of all we have to substitute with Hg group and then we can substitute by Br group. The 2-chloropyridine is a liquid boiling point 168 degrees Celsius, while the 3 isomers boils at 148 degrees Celsius. They are pleasant smelling liquid in comparison to the parent compound pyridine and are also more basic. The most important reactions of halopyridines are nucleophilic substitution and elimination to give pyridines. We will discuss in coming slides. The halo group at the position number 2 and 4 are more reactive than that at position number 3 and readily undergo hydrolysis in the presence of a base. 4-chloro and 3-chloronitropyridine is rather very liable and it is hydrolyzed even in warm water. Halopyridine do not readily form Grignard reagent by direct reaction with magnesium. Pyridyl Grignard reagent and pyridyl lithium compounds are both prepared by reaction of halopyridine, first of all with alkyl magnesium halide or alkyl lithium compounds, that is by entrenchment method. The cyano group displaces the halogen at the position number 3 and much more rapidly than position number 2 and position number 4 to form nicotinonitrile. 2 and 3 bromopyridines undergo photochemical SR nickel reaction in liquid ammonia with potassium enolates of acetone and many other ketones to yield pyridine derivatives via free radical mechanism. Here you can see, first of all, this group get attacked by this pi electron towards it at 350 nanometer and liquid ammonia 300 degree Celsius, and you will get 3 pyridyl acetone. And here also you can see cyclohexanone when reacts in the same manner via free radical mechanism. Here you will get 2,2-pyridyl cyclohexanone. So, nucleophilic substitution takes place in both reaction, here also and here also. Next derivatives of pyridines are aminopyridines. 2-aminopyridine is most conveniently prepared by Shishy-Babin reaction. In this reaction, a small amount of 4-isomer is also obtained. All isomeric halopyridines can be converted to the corresponding aminopyridines by the action of ammonia and a suitable catalyst at elevated temperature. Here you can see 2-chloropyridine when reacts with ammonia at 250 degrees Celsius in presence of nickel sulfate. This chloride will substituted by this amino group at alpha position. And here again, but the temperature is 140 degrees Celsius, and here the temperature is 220 degrees Celsius. Nickel sulfate is replaced by copper sulfate, and here it is replaced by zinc chloride at position number 4. So, different products are found when we are taking different reagents and different temperatures with ammonia. All the 3 monoaminopyridines can also be obtained by the Hofmann reaction on the corresponding pyridine carboxyamides. The monoaminopyridines are solid. 2-aminopyridine have melting point 50 degrees Celsius, while 3-aminopyridine have melting point 65 degrees Celsius, and 4-aminopyridine have melting point 157 degree Celsius. They all are quite basic and form stable aryl alkaline salt by protonation of ring nitrogen atom. There exists also a marked difference in the properties of 3-amino and 2 and 4-aminopyridine because of the later displayed tautomerism to hydroxypyridine. Here you can see the tautomerism in both the at position number 2 and position number 4. Electrophilic substitution on 2-aminopyridine is controlled by NH2 group, and this directs the incoming group to the 5th position. Here you can see the 3-aminopyridine behaves as a normal aromatic amine and like aniline can be diazotized at 0 degree Celsius and give all the usual reaction of a diazoxime salts, that is elimination reaction or substitution reaction. Here you can see when it reacts with bromine and acetic acid, bromide group is substitute over here, and when it reacts with nitrating mixture, that is HNO3 and H2SO4, nitro group is introduced over here by substitution reaction, electrophilic substitution reaction. The 2 and 4-aminopyridines can be diazotized only under strongly basic conditions. Now, the very important derivative of pyridine N oxide. Why it is important? Because it is the reactions with pyridine N oxides are feasible. Which kind of reactions are more feasible? Electrophilic substitution reaction and nucleophilic substitution reaction. Why it is so? First of all, we discuss pyridine N oxides, the structure of pyridine N oxide. We need to activate the ring, pyridine ring, with an electron rich substituent, and that can be later be removed. We also need to stop the nitrogen atom which is in pyridine reacting with the electron rich substituent because of electron withdrawing nature of nitrogen atom. So, we also need to stop the nitrogen atom reacting with the electrophile. How can we do that? All of this can be done with a single atom. And because the nitrogen atom is nucleophilic, pyridine can be oxidized to pyridine N oxide, very interesting compound, with reagents such as hydrogen peroxide in acetic acid. So, what we are doing here, we are making it more susceptible towards both kind of reaction. nucleophilic substitution reaction as well as electrophilic substitution reaction. This is pyridine N oxide. You can see the structure. This is pyridine N oxide because this oxygen atom is attached to this nitrogen by donation of lone pair of electron of nitrogen towards oxygen. Pyridine itself is a stable towards the action of oxidizing agent, but towards per acids it behaves like tertiary amines. So, the unshared pair of electrons on nitrogen atom links an oxygen atom in a coordinate linkage. You can see this is a coordinate bond and forming an amine oxide. So, here we can see tertiary amine oxide. With perbenzoic acid, pyridine yields pyridine N oxide in a yield of 85%. Here is the reaction. This is when pyridine reacts with benzoic per acid in the presence of chloroform at room temperature, it will give you pyridine N oxide. Now, picolines 2, 3 and 4 picoline N oxides, 2, 3, 2, 4 and 4, 6 lutein N oxide and isomeric halo N oxide can be prepared in a similar manner by direct oxidation with per acid of pyridine. Pyridine N oxide is a colorless solid, melting point 66 degrees Celsius, and it is soluble in water and in most organic solvent. What a beauty! It is soluble in water as well as in organic solvent. That is why it is very interesting compound. 2 picoline N oxide boils at 127 degrees Celsius, 3 picoline N oxide at 33 to 36 degrees Celsius, and 4 picoline N oxide boils at 186 to 188 degrees Celsius. Pyridine is a weakly acidic. It has a pKa value of 5.17, whereas pyridine N oxide has a pK value of 1.90. You can see the difference between pyridine and its derivative pyridine N oxide, and this difference is basicity, considerable basicity. The difference shows the considerable basicity among these two compounds, pyridine and pyridine N oxide. The donation of electrons from the oxygen into the ring is significant and is apparent from the dipole moment value. You can see the dipole moment of pyridine, it is 2.23 d, while for pyridine N oxide it is 4.30 d. So, you can see the difference of dipole moment, and which is very interesting a part for the reactivity of nitrogen pyridine N oxide. So, we have discussed the many derivatives of pyridine, pyridine N oxide, the alkyl pyridine, aryl pyridine, halopyridines. Hopefully, you have understood about the derivatives of pyridine. Thank you so much. In the previous part of derivatives of pyridine and indole derivatives, we have discussed about the alkyl aryl pyridines, about the halopyridines, and very interesting derivative of pyridine, that is pyridine N oxide. Why it is so interesting? Because it gives readily electrophilic as well as nucleophilic substitution reaction. And why it is so? Any feasibility of a reaction depends upon the stability of intermediate, and here you can see the reaction intermediate or stability of pyridine N oxide. Here are 4 resonating structures. So, more the resonating structure of an intermediate, more feasible will be the reaction, whether we are talking about electrophilic substitution reaction or we are talking about nucleophilic substitution reaction. We have discussed about dipole moment, the difference of dipole moment between pyridine and pyridine N oxide. This value is considerably less than anticipated, and if you are talking about this sum, this is the 6.6 G of dipole moment of pyridine and pyridine N oxide. So, a significant contribution from the resonating structure we have discussed. These structures also imply an increased susceptibility of the ring in pyridine N oxide to electrophilic substitution reaction. The pyridine N oxide molecule is quite versatile because of its polarizability. You have seen that nitrogen contains positive charge while oxygen contains negative charge. The N oxide group can function both as electron acceptor and as an electron donor depending upon the demand of the reagent. This dual behavior leads to some interesting reactivity patterns in N oxide chemistry. As a consequence, both nucleophilic and electrophilic substitution occur with ease with 2 and 4 positions. Chlorination of pyridine N oxide with sulfuryl chloride gives a mixture of 2 and 4 isomeric chlorine chloropyridine. 2-picoline N oxide with phosphorus oxychloride yields 72% 4-chloro-2-picoline. Direct chlorination and bromination to form halopyridine N oxide is difficult, and you can see how the reaction took place with pyridine N oxide, picoline, and with chloride ion in phosphorus oxytrichloride. This kind of intermediate and rearrangement took place. You can see the kind of rearrangement and you can see the product. Pyridine N oxide are nitrated more easily than the parent pyridines. Nitration of pyridine N oxide gives a high yield of 4-nitropyridine N oxide. You can see the reaction. The corresponding 2 isomer is not obtained by direct nitration but by oxidation of 2-aminopyridine N oxide. In contrast, sulfonation of pyridine N oxide is not easy and takes place only under severe condition in presence of oleum or HgSO4, mercuric sulfate, and a temperature of 220 and 240 degrees Celsius. Pyridine N oxide 3-sulfonic acid is obtained when reacts with these reagents. This drastic change in orientation from nitration is probably due to the formation of species A. You can see this kind of intermediate is formed and in which electron donating property of oxygen is suppressed. Why it is suppressed? You can see here because it attached to this SO3 negative anion. Pyridine N oxide reacts with acetic anhydride on heating to yield 2-acetoxypyridine. Here is the reaction, you can see how it took place, and the rate is slightly decreased by the addition of sodium acetate and no gaseous products such as methane or carbon dioxide are evolved. And this kind of mechanism over here, you can see this is acetic anhydride. First of all, this kind of intermediate will form, followed by rearrangement will give you this, and after hydrolysis it will give you this kind of product. 2-methylpyridine N oxide similarly interacts with acetic anhydride. 2 and 4-methylpyridine N oxide, similar to other reactive methylene compounds, can be nitrosated and participate in the Claisen condensation. You can see the products. This is the Claisen condensation product. What will be the possible mechanism? Nothing but first of all, this active methylene compound, first of all, will give you carbon ion and it will attack to this methylpyridine N oxide. The anions derived from pyridine N oxide serves as useful intermediates as shown below. You can see this lithium can substitute by carboxylic group, can substitute by bromide when reacts with carbon dioxide and followed by hydrolysis, or when reacts with bromine. Pyridine N oxide can be reduced by a variety of reagents to regenerate the parent pyridines. Such reagents include catalytic hydrogenation over ranitidine, iron and acetic acid, or sodium borohydride and aluminum chloride. The reagents of choice, however, are trivalent phosphorus compound such as triphenylphosphine, triethyl phosphite, dialkyl sulfoxylates and phosphorus trichloride in chloroform. Pyridine N oxide is also deoxygenated to pyridine on irradiation. Irradiation means when react with photons, or on treatment with hexamethyl disilane at 0 degree Celsius. Here you can see this nitrogen N oxide can convert it to pyridine, or we can say deoxygenated, removal of oxygen from this N oxide, pyridine. Analogous to certain halopyridines, appropriately substituted halopyridine N oxide react with strong bases to form 2,3 and 3,4 pyridine N oxide. 2-chloro or 3-bromopyridine N oxides results in 2,3 pyridine N oxide, which on treatment with potassium amide in liquid ammonia gives a mixture of 2 and 3 aminopyridine N oxide. The yield will be 5 to 10%. Here you can see the reaction, how the substitution takes place via this. You can see this is a benzyne or heterine we have discussed in pyridine. This is the heterine kind of intermediate formed in this reaction. On the other hand, 3-bromo 2-ethoxypyridine N oxide under these conditions yields the 3,4 pyridine. In the presence of a secondary amine in water and pyridine N oxide, ring is opened on ultraviolet irradiation to lead an unsaturated nitrile. Here you can see the unsaturated nitrile. The reactivity of a 2 and 4 alkyl pyridine can be increased by conversion to the corresponding pyridinium salt or pyridine N oxide. The result of this side chain activation is generally reflected in the need of a much milder base to affect condensation. Here you can see how condensation takes place in presence of pyridine and after refluxing. Pyridine N oxides in the presence of acyl halide react with enamines as shown below. This is the kind of reaction. Here you can see what kind of reaction takes place over here. With benzene sulfonyl chloride, pyridine N oxide yields beta benzene sulfonin oxy derivatives. An alkyl nitrite and sodamide in liquid ammonia with alpha benzyl pyridine N oxide provides an oxime. Here you can see this kind of intermediate will form, and this is the oxime derivative of N oxide pyridine. Next derivative of pyridines are hydroxypyridine, that is when hydroxyl group is attached to the pyridines, or we can say pyridinols. The Keto-Enol Tautomerism is well known in organic chemistry. The keto form is believed to be more stable than the enol form. The 2 and 4 hydroxypyridines also exist in tautomeric forms with the 2 and 4 pyridines as shown. You can see this kind of tautomerism in organic chemistry, and in enols, or we can say pyridinols, you can see how the tautomerism is present. This is the enolic group and this is the ketonic group in position number 2 and position number 4. Comparison of the ultraviolet spectra of the reference compounds 2-methoxypyridine and 1-methylpyridine clearly established that in polar solvent the 1-oxo form is preferred. Further, the keto forms behaves as amide. The case with 3-hydroxypyridine is different as it exists to a considerable extent in solution as a pyridinium oxide zwitterion. On ammonolysis, what is ammonolysis? Nothing but when react with ammonia, alpha and gamma pyrrones are converted to alpha and gamma pyrrodidones respectively. You can see how the reaction takes place. 1,3-diene cyclazides, this is 1,3-diene cyclazides on thermolysis, it means when react with high temperature, results in substituted 2-pyridones. Substituted 2-pyridones, that is this kind of a structure, may also be obtained by thermal rearrangement of propyrylic pyrrolidine pseudourea. We will discuss in next slide the kind of reaction, and the latter can be obtained by potassium alkoxide catalyzed reaction of secondary propergyl alcohol and cyanopyrrolidine. Here you can see this is the propergyl alcohol, this is the cyanopyrrolidone. First of all, what happens here? You can see potassium ethoxide what kind of reaction proceed? You can see here what kind of rearrangement is present over here. This lone pair can attack to this because this pi electron get attracted to this because of this rearrangement, and so we can see over here this sigma tropic rearrangement here, and this kind of product will form after subsequent reactions or rearrangement. 2 and 4 pyrinidols behave similarly in their chemical properties. Unlike 3 pyridinol, however, they are less phenolic in character. Why? Because it is attached to this conjugated system. On treatment with diazomethane, the 2 isomer yields mainly the orthomethyl derivative, while the 4 isomer yields the N-methyl derivative. Phosphorus pentachloride and thionyl chloride can replace the hydroxyl group by chlorine. You can see the reaction. 3-pyridinol behaves as a typical phenol and gives a purple color with ferric chloride. It undergoes electrophilic substitution reactions such as halogenation, nitration, sulfonation, and predominant attack at position number 2. 3-pyridinols also form ethers similar to phenols. 3-pyridone leads to bicyclo 2,2,0 pyran 2,1 on direct irradiation, and you can see this is the bicyclic compound when react with ether on irradiation. Next derivative of pyridines are pyridine aldehyde and pyridine ketones. That is when pyridine having aldehyde group and having ketonic group. Pyridine aldehydes have been prepared by a variety of methods. Pyridine 2-aldehyde may be prepared by ozonolysis of 2-pyridine stilbenzol and reduction of the ozonide. You can see this, when react with ozone, first of all ozonide complex will form, and followed by reduction with zinc dust, it will give you this kind of aldehydic pyridine at position number 2. All the isomeric pyridine carboxyldehydes can be prepared by the following reaction. You can see what happens here. First of all, it get reduced to alcoholic group, and then when oxidized with selenium oxide, it will give you pyridine aldehyde. Another important preparation involves the reaction of pyridine nitrile with chromous acetate to picolyl amines followed by oxidation. You can see this is the picolyl amines, and on oxidation it will give you pyridine aldehyde. Substituted pyridine carboxyldehydes have been prepared by pyrolysing 2-bis methyl thiomethyl pyridine S oxide as shown below. Here you can see the reaction, how it took place. The aldehydes closely resemble aryl halides largely because a carbonyl compound cannot interact mesomerically with pyridine nitrogen atom. It thus adds sodium bisulfite, undergoes benzoin condensation and Cannizzaro reaction. Here you can see the benzoin. When we see in aldehydes and ketone benzoin form, here we can say pyridine will formed when reacted with potassium cyanide and ethanol at room temperature. Pyridyl ketones are obtained by retreating cyanopyridines with Grignard reagent. So, first of all you can see the Grignard complex will form, and subsequent hydrolysis will give you ketone. A number of ketones have been prepared by Zapp-Klingman reaction. What happens here? This involves the reaction of a diazonium salt with a pyridine carboxylic acid to form an aryl hydrazone, and the ketone is obtained by hydrolysis. Pyridyl ketones gives a reaction expected to the aromatic ketones. Here you can see the preparation of ketone, pyridine ketone. They condense with the usual carbonyl reagent to form well-defined derivatives. They also behave normally toward the action of oxidizing agent. Thus, 2-acetyl pyridine undergoes the normal iodoform reaction we have discussed in aldehyde and ketone. The 2-acetyl pyridine undergoes the Dargens reaction, it also we have discussed with alpha halogenoesters. Next derivatives of pyridine are pyridine carboxylic acid, or we can say picolinic acid. The pyridine carboxylic acids and their derivatives are present in many natural products, for example, in alkaloids, in vitamins, in coenzymes, etc. They are obtained by direct oxidation of corresponding monoalkyl pyridines, quinolines, isoquinoline, and hydrolysis of cyanopyridines. The pK values of acid indicate that they exist mainly in zwitterionic form in aqueous solution, and this may be pattern responsible for their facile decarboxylation of these derivatives. These acids are slightly more than benzoic acid. Here you can see the structure of pyridine carboxylic acid when it present in this alpha position, beta and gamma position, and this is benzoic acid. Now, significance of pyridine derivatives in our daily life, or you can say biological importance of pyridine derivatives. Are they important biologically? Of course, yes. Why it is so? You can see in the coming slides or in this slide also. Pyridine and piperidine derivatives occur in nature abundantly. And if you remember, I have discussed in the heterocyclic compound while discuss about the pyridine that it is the first heterocyclic compound discovered. Nicotinic acid was isolated from yeast and also from bran. It is an additional member of vitamin B complex. It is formed in vivo from essential amino acid tryptophan in animals. Nicotinamide is essential for curing the disease pellagra in human being. It occurs in liver and is excreted in human urine as glycine conjugate nicotinuric acid. Protein enzyme function as catalyst in chemical reaction of living systems. In many cases, they react with substrate only when a second component referred as a coenzyme is also present. One of the more important coenzyme is nicotinamide adenine dinucleotide, or we can say NAD. With the aid of other enzyme, this plus takes place with the great ease in electron transfer reaction. The nicotinamide portion abstract a proton ion and is reduced to 1,4-dihydropyridine counterpart NADH plus and the substrate undergoing oxidation. NAD function as a reducing agent. The pyridyl methanol derivatives are B6 or pyridoxine, pyridoxamine and pyridoxine, all of which occur in combined form. The most important role of these substrate in biological system centers around transmission and decarboxylation reaction. The pyridine ring occurs in nature in many alkaloid, and the best known of these are tobacco alkaloid such as nicotine, anabasine and viscirine. Another important pyridine alkaloid, buccanine, is obtained from a plant which is used in the preparation of the treatment of rickets, which happens in children because of deficiency of vitamin D. So, we have discussed about the pyridine derivative. Now, the derivatives of indole. We have discussed in previous lecture about the indole. Now, the derivatives of indole. What is indoxyl? Indoxyl is the 3-keto tautomer of 3-hydroxy-indole, though it exists almost entirely in the carbonyl form. Here you can see this is keto form, and by the transfer of proton you can see this is the enol form, means tautomerism. It is an important intermediate in the synthesis of indigo and is also of biochemical importance because of its occurrence in the form of its glucoside in certain plants. It may be prepared according to the following scheme from aniline. Here you can see this is the aniline, this is chloroacetic acid in presence of NaOH. First of all, it will give you this kind of addition product, and followed by hydrolysis it will give you indoxyl. You can see this is the keto form. Indoxyl is a yellow crystalline solid having melting point 85 degrees Celsius. It gives a strong unpleasant odor and is soluble in hot water. So, you can recognize it easily. Indoxyl also deprotonates to a carbonyl group like oxy-indole and thus condenses with aldehydes and ketones. With methyl iodide in a sodium hydroxide, indoxyl is alkylated at position number 2 to yield 2,2-dimethyl indoxyl. In alkaline solution, indoxyl is converted to indigo. Indoxyl in presence of zinc and acetic acid is reduced to indole. Here you can see when it reacts with benzaldehyde what kind of addition product will form. Substituted product will form over here. Next derivative of indole is isotin, or we can say dioxy-indole. Isotin is an indole derivative containing keto group at position number 2 and position number 3. Here you can see this is the structure of isotin, and these are the oxygen atoms present at position number 2 and position number 3. Early studies on action of oxidizing agent on indigo lead to the discovery of an oxidation product to which the name isotin was given. and could be obtained in 70 to 80% by the action of chromic acid on indigo, and it has been prepared by other methods also. The most general method is due to the Sandmeyer, in which aniline and chloral hydrate first form iso-nitroacetanilide in the presence of hydroxylamine. This subsequently cyclizes in the presence of sulfuric acid, and here you can see the reaction. This is pyridine, this is chloral. Here first of all what happens, it will gives you this kind of product first of all. So, proton will substituted by this reactant, and followed by hydroxylamine and hydrolysis, it will give you iso-nitroacetanilide, and with H2SO4 it will give you acetylene. According to another synthesis, nitrobenzoyl cyanide prepared from ortho nitrobenzoyl chloride and silver cyanide is hydrolyzed and then reduced with ferrous hydroxide to orthoaminophenyl oxalic acid, and acidification results in acetylene. You can see this is the structure of ortho nitrobenzoyl chloride. When it reacts with silver cyanide, it will, what happens here, this chloride ion gets substituted by cyano group followed by ferrous hydroxide, it will give you this kind of carboxylic group, and then reduction of this nitro group will give you orthoaminophenyl oxalic acid, and when it reacts with HCl it will give you acetylene. Derivatives of acetylene can be conveniently prepared from N-substituted anilines. Here you can see the structure of N-substituted anilines. The two hydrogen atom get substituted by 2R group and oxalyl chloride followed by cyclization with aluminum chloride. So, this is the oxalyl chloride. First of all, this kind of substituted product will form, and when it reacts with aluminum chloride, it will give you this kind of substituted acetylene. Acetylene forms red needles, melting point 200 to 201 degrees Celsius, and can be crystallized from hot water or can be from alcohol. It is basic in nature, dissolves in concentrated HCl and H2SO4. With perchloric acid, it forms stable perchlorates. The nitrogen hydrogen is sufficiently basic in nature and it will form salts with sodium or potassium metal. Halogenation results in the formation of 5-haloacetylene derivative. In the fifth position, if fifth position is occupied, then the electrophile will take place the seventh position. Chromic acid or hydrogen peroxide oxidation results in acetoic anhydride, which on subsequent hydrolysis and decarboxylation will yield you acetoic acid. Acetylene condenses with thiophene in concentrated sulfuric acid to give a deep blue color due to the formation of indophenine, and you can see the structure of indophenine. These are two acetylene, and these you can see two structure of thiophene. This is used as a test for detection of thiophene. The alpha position of thiophene molecules are utilized in the reaction, therefore, alpha substituted thiophene will not respond to this test. Here you can see the bond will form at position number alpha. If alpha is occupied in thiophene, so it cannot be detected by this test or when react with acetylene. The carbonyl group at position number 2 on the other hand is adjacent to the heteroatom and is stabilized by resonance. It thus behaves as a typical amide in its properties. The heterocyclic ring is opened by alkalis and the intermediate so obtained can condense with ketones to give quinoline derivatives. Here you can see the quinoline derivatives. This is the structure of quinoline and 3 methyl groups are attached to this quinoline. Next derivative of indole is indigo. This is, you can see the structure of indigo. Indigo occurs in plants, for example, Indigo fera tinctoria as indican, the beta glucoside of which yields indoxyl and glucose on hydrolysis. Air oxidation of indoxyl then gives indigo, which is used as a dye, as a wet dye. Indigo is nowadays produced synthetically and is reduced to leuco. This is the structure of leuco, you can see nothing. What is the difference between these two structure? Here you can see the oxygen atom and here you can see the hydroxyl group. So, you can see it contains the tautomerism. It can oxidize by exposure to air or by more rapidly by an oxidizing agent such as sodium perborate. Indigo can be prepared by Deccan process on 3-formyl indole. This is the structure of 3-formyl indole. This consists in the treatment of 3-formyl indole with hydrogen peroxide. Here you can see when hydrogen peroxide reacts with this, what happens? This aldehyde group attached to this group, nucleophilic addition reaction will take place over here because of this carbonyl group, and followed by rearrangement. What kind of rearrangement? You can see because of this electron withdrawing nature, these electrons get attracted by this oxygen atom and a 3-membered, or you can say epoxide ring is formed over here, followed by subsequent rearrangement. You can see what kind of it can attracted by this carbon because of breaking of this bond. So, a electrophilic center is produced over here and this kind of product will form, followed by hydrolysis will give you indigo. Indigo has also been obtained by an electrochemical method. For dyeing purposes, indigo is reduced to the yellow leuco-indigo. We have discussed the structure of B by sodium hydrosulfide. Next derivative of indole is 1-hydroxy benzotriazole, or we can say in short HOBT. HOBT is an important reagent in peptide synthesis. It is added to many reactions where an activated ester of one amino acid is combined with the free amino group of another. It was first made in 19th century by a remarkably simple reaction. The structure of 1-hydroxy benzotriazole appears quite straightforward except for the unstable N-oxygen single bond. But we can easily draw some other tautomers in which the proton on oxygen and the only one is the heterocyclic ring can be replaced on some of the nitrogen atom. So, here you can see the tautomerism. Here you can see alcoholic group is over here, and when this kind of structure is also present and this kind of structure. So, what can you see over here? The different structure tautomers in HOBT. These are the more structures. These structures all are aromatic in nature, and the second and third are nitrones. The third structure looks less good than the other two. HOBT comes into play when amino acid are being coupled together in laboratory. The reaction is an amide formation. The amino acyl chloride cannot be used to make polypeptides. They are too reactive and they lead to side reactions. Instead, activated amino esters with good RO leaving groups are used as phenyl esters. It is even more common to form deactivated ester in the coupling reaction using as a coupling reagent, the most common being DCC. What is DCC? Dicyclohexyl carboimide. DCC reacts with carboxylic acid like this. You can see how can it reacts with this. The product ester is activated because substitution with any nucleophile expels this very stable urea as a leaving group. You can see the leaving group is formed over here, and what kind of reaction will take place over here. This is the nitrogen with lone pair of electron, and it can attack to this carbonyl carbon because of the electron withdrawing nature of because of this oxygen atom. First of all, you will get this kind of addition product, and you will get the dicyclohexyl urea also as a side product. The problem with attacking this ester directly with amino group of the second amino group is that some racemization of active ester is often found. A better method is to have a plenty of HOBT around. It intercepts the activated ester first, and the new intermediate does not racemize, mostly because the reaction is highly accelerated by the addition of HOBT. The second amino group protected on the carboxylic group attacks the HOBT ester and gives the dipeptide in a very fast reaction without racemization reaction. You can see how the reaction took place. So, we have discussed about the derivatives of pyridine, we have discussed about the indole derivatives of indole derivatives, and this is the summary. We have discussed about the electrophilic substitution reaction of pyridine. We have discussed about the derivatives of pyridine, alkyl, aryl, halopyridine, aminopyridine. We have discussed about the structure of pyridine N-oxide and why it is good in both kind of reaction, that is electrophilic as well as nucleophilic reaction. We have discussed about hydroxypyridine, pyridine aldehydes and ketones, pyridine carboxylic acid, significance of pyridine derivatives and the derivatives of indole also, for example indoxyl, icetin, indigo and HOBT. Hopefully you understood these lecture. Thank you so much.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Vandana for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.
Thank you.